the time value of money is most likely the most important topic in finance. In finance, people lend money, so they give money today and they get it back at some other point, or people borrow money, in which case they receive money today and repay it at a future date. So all this has to do with time value of money. So let me ask you a simple question. Is a dollar today the same as a dollar a year from now? That is, would you give me a dollar today if I promise to give you back a dollar a year from now? And let's assume that you kind of regard me as completely honest and you're very sure I would return the dollar. But still, you'd probably say no, because you would earn interest on the dollar. So when you lend money, you also expect to get back that money plus a little more. And 2 years from now, you would earn more interest on the dollar and also interest on the interest that you earned during the first year. So when you invest money, you not only earn interest on that money invested, but also interest on the interest that has been previously earned. So when you invest money, and let's say you invest a dollar today, and a year from now, you get back a dollar into 1 plus R, then R is called the rate of interest. This 1 plus R, the R in the 1 plus R is the rate of interest. Similarly, when you bring money from the future back to the present, for example, you pay $1 divided by 1 plus D for $1 which you will receive in the future. So today's value, say, equals $1 divided by 1 plus D. That D is called the rate of discount. This is the rate of discount. So there are two rates. One is the rate of interest, which is, as you move forward in time, the rate which you receive. And the other is the rate of discount. That is when you bring money back from the future to today. That is called the rate of discount D. And a simple question is, what is the relationship between rate of return and rate of discount? And the answer is they are the same. And why are they the same? Well, when you're moving forward 1 year, you're multiplying by a factor of 1 plus R. So multiplying by a factor of 1 plus R as you move forward 1 year is the same as dividing by 1 plus R when you come back 1 year. It's like you say, what is the exchange rate between Japan and US? Well, to take money from US to Japan, to convert dollars to yen, you multiply by 100. Approximately, that's what the dollar-yen exchange rate is. So you multiply by 100. And when you want to bring money from Japan to the US, you take the amount in yen and you divide by 100. So the rate of return, which is the rate for moving forward, is the same as the rate of discount, which is the rate for moving back. When you move forward, you multiply by 1 plus R. When you move back, you divide by 1 plus D. And these two numbers should be the same. Now, I should clarify something. Let's say you go to a bank and you say, I want to invest money. So you give them money and you get it back, let's say, after a year. And that is moving money forward in time. So they tell you the interest rate they'll give you is maybe 1% on a checking account, 0.5%. And then you say, hey, how about moving money back in time? That means you receive money today and you repay it later. You tell the bank, well, my professor told me that the rate of return and rate of discount should be the same. So if I can invest money at 0.5% with you, then you should allow me to borrow money at 0.5%. And the bank will say, no. That can't happen. And so what's happening, I mean, what is different about that than over here, what I was speaking about? Well, here I was speaking about how you value money at different points in time, how you look at money at different points in time. There, when you're borrowing from the bank or you're investing with the bank, there are other issues, like there are information issues, there are transaction costs, all these other things, and that lead to a divergence between the rate of return which you can receive from the bank and the rate at which they lend you money. This is about how you value money at different points in time, and for you personally, the rate at which you value money moving forward should be the same as the rate at which you value it moving back. So what we have till now is that when you move forward in time, the amount of money increases by 1 plus R every year you move forward. And compound interest, the interest that you earn, will earn interest in further years. And that is how the world works. I mean, interest is money. So if you invest something for a year, and whatever interest you get, the next year, if you want to keep that investment, you should receive money on that interest too. So if every year it increases by a factor of 1 plus R in compound interest, then over n years, it should increase by a factor of 1 plus R to the power n. So if your initial principal is P, then, and the rate of interest is R, and n is the number of period, then after n periods, you're going to have P multiplied by 1 plus R to the power n. Similarly, when you are discounting, every year that you move back, you divide by 1 plus D or 1 plus R. And if you move back n periods, then let's say you take $1 and you move it back n periods, the value of it today, which is called present value, would equal $1 divided by 1 plus R to the power n. So every year moving back, the value decreases by a factor of 1 plus R, and for n years it will decrease by the factor 1 plus R to the power n. Now that we have learned how to find the present value of a particular cash which occurs at a point in the future, what we are now going to do is we are going to look at not cash which occurs at one point in the future, but a series of cash flows. And one very interesting series of cash flows is called an annuity, which is a constant cash flow at the end of every period for a fixed number of periods. Now, of course, it's very common, this kind of cash flow. For example, house mortgages are annuities, or even if you purchase a car, you may have a 5-year financing plan where you make a fixed amount of payment every month for 5 years. So that would also be an annuity. If the cash flow continues forever, which is less common, it is called a perpetuity. Now, using what we have learned about time value of money, we are going to find what the value of a perpetuity is. So, a perpetuity has a cash flow C every period, and if the discount rate is R, then the present value of the perpetuity will be the sum of the cash flow which occurs next period and the one which occurs 2 periods after that, and the 3rd period and the 4th period, and so on till infinity. Or the cash flow which occurs next period will have a present value today of C divided by 1 plus R. The cash flow which occurs 2 periods from now will have a present value of C divided by 1 plus R squared. and the third period will be C divided by 1 plus R cube, and so on. And this is actually a geometric series. This is like high school algebra. So the sum of this is simply reduces to C divided by R. So that is the value of a perpetuity, which pays an amount C every period and has a discount rate R for every period. It is simply C divided by R. Now, students often make this mistake. They get confused by whether it should be 1 plus R or R. If you just have a cash flow in one point in time in the future, then you divide by 1 plus R to the power n, where n is the number of periods to that point in time. So there you use 1 plus R. However, when you have a perpetuity, which is a series of cash flows, and you're summing them, you're getting the present value of that entire series of cash flows, then, and only in that case, would you be dividing only by R. So you'll have C by R for that case. Now that we have the formula for a perpetuity, you would like to also know the formula for an annuity. And what you can think of an annuity to be is a perpetuity which goes on forever, and then another negative perpetuity which starts at a future point in time. And if you add these two together, the result should be an annuity which is a series of constant cash flows for a finite number of periods. And the perpetuity which goes on forever would have a value of C by R. And the perpetuity which starts after n periods would also have a value of C by R, but at that nth period. So today's value would be that value C by R divided by 1 plus R to the power n. And you subtract the second perpetuity from the first one, and this net gives you the annuity, and that becomes equal to C by R into 1 minus 1 divided by 1 plus R to the power n. And so this is a useful formula. It's it's annuities, and you'll see annuities everywhere in the financial world. But it's good if you remember this formula. And there are also these things called financial calculators now, which will compute annuities for you. So it's nice if you remember it. Otherwise, you always have these financial calculators. Here we have a simple example of an annuity. There are 3 $500 cash flows, one at the end of the first year, one at the end of the second year, and the third one at the end of the third year. And the discount rate is 10% per year. So the question is, what is the present value of this annuity? Well, using the annuity formula, you will have 500 divided by the discount rate 10%, so that's 0.10, into 1 minus 1 plus the discount rate, that will be 1.1, to the power n, and n here is 3 years. So that should be the value of this cash flow today given by the annuity formula. And if you compute this, it will turn out to be equal to 1243.43. So the 3 cash flows of 500 each. So you multiply 500 by 3, so you get 1500, but it's not 1500 in today's value because some $500 which comes at a point in future today has a value lower than that because of discounting. That's just time value of money. money in the future has a lower value compared to money in the present. So the value of the money in the present is $1,243.43. Now, if just to kind of check and show you that this is actually the value, present value of this cash flow, what I'm going to do is I'm just going to compute the present value without using the annuity formula. So I have three cash flows of 500. And the first one, I'm going to discount by 1 year because the first one comes after a year. And that, when I divide 500, so I'm going to divide by 1.1. That's the discount factor, 1.1. And this will give you a value of that cash flow today of $454.55. So when I say 1.1 is the discount factor, the discount rate is 0.1, that's 10%. And to get the discount factor, you add 1. So you add 1 to the discount rate, and that gives you the discount factor, and you divide by the discount factor to get the present value. The discount factor for this cash flow 2 years from today is going to be 1.1 squared. So we are going to divide this by 1.1 to the power 2. So you divide 500 by 1.1 squared, and what you get is $413.22. So that's the present value of the cash flow of 500, which you get 2 years from now if the discount rate is 10%. The third cash flow of 500, you're going to discount by 3 years. So the discount factor is going to be 1.10 to the power 3. And that is going to have a value today of 375.66. So these are the individual values of the three cash flows that you get a year, 2 years, and 3 years from now. And to get the value of the stream of cash flow, you are going to add these values, because the value of a cash flow which occurs at multiple points in time is the sum of those values. So the sum of the present values, and you're going to add these three present values to get the total value of this cash flow. And when you add it, you'll find that you get $1,243.43. And which is what also the annuity formula gave you, because the annuity formula is right. So what you just saw is that the annuity formula gives you the same answer as the one you get from first principles, where you took the present values individually and added them up. Of course, that you can do for situations where there are three cash flows, but most of the time there are a lot more cash flows, and so the annuity formula makes life simple. For example, when you have 60 cash flows, you don't want to be adding these 60 cash flows separately. Instead, you use the annuity formula. And here, the cash flow is $500 a month, and the discount rate for a month is 0.7%. So, you want to know what the present value is? Well, the present value by the annuity formula will be 500 divided by, 0.7% is going to be equal to 0.007, because percent means by 100 per 100. So you divide that by 100 to get 0.007 into 1 minus 1 divided by 1.007. And how many periods? Well, 60 periods. So this should be the present value of the annuity, and this will turn out to be 71,428.57. So that's 500 divided by 0.007 into 1 minus 0.65801. And that will equal $24,427.86. So, of course, if you took it without discounting, you would have 500 into 60 would be 30,000. However, because these are cash flows in future points in time, the present value is going to be less than that, and it's actually going to be 24,427.86. Now we are going to have even more fun moving money across time. We'll start with another annuity, and then we'll move all the value to today, and then we'll move it forward. So we'll just show that we can basically do a lot of things once we've understood time value of money. So here we have an example, and you deposit $1,000 at the end of each year for 30 years, and the account pays 7.5% interest. Now, 7.5% is what the stock market is supposed to pay. And so the question is, how much money will you have at the end of 30 years and 50 years? Now, we have the formula for an annuity, which is a stream of cash flow which has been brought back to the present. Now, to move the stream of cash flow to the future, all we really need to do is simply move that present value to the future. I'll show you how to do it now. So, if I was to draw the timeline, it would look something like this. So, let's say this is today, and this goes on till about you get to 30 years. And the second part of the question says, what if it was 50 years? So this is today, and you're going to deposit $1,000 every year, and that's going to go on for 30 years. And in the second part of the question, you're going to deposit $1,000 a year every year for 50 years. So, the first part of the question, to see how much this money will be at the end of 30 years, we first calculate the present value of this money. So, the present value of this money will be 1,000 divided by the rate of interest, which will be 0.075 into 1 minus 1 upon 1.075 to the power 30. And when you calculate this, you will have 11,801 and 39 cents. So that's the present value of this money. Now, we moved it to the present, all these cash flows. So we moved all this money here. What we actually wanted to do was that we wanted to move all this money here. So, how do we know what the value would be when you move this money here? Well, think about it this way. Suppose you want to move money from Japan to Brazil, right? Let's say this is Japan and this is Brazil. You want to move money from Japan to Brazil. Alternatively, what you could do is you could move the money from Japan to US and then from US to Brazil. Because you know how much the money, that Japanese money is going to be worth in US, and assume no transaction costs. So you know what the Japanese money is going to be worth in US, and you also, because you have the annuity formula, so you're using the annuity formula to get all these different cash flows back to this point in time. And you also know what the rate is from here to here. What is the rate from US to Brazil, or from today to 30 years forward? Well, it is 1 plus the rate of return to the power 30. So it's the yearly factor for growth to the power 30. So this money would become, so value, let's say at 30 years, will be equal to this amount into 1.075 to the power 30, and that equals 103,399. Similarly, for 50 years, you can find the present value to be 1,000, again divided by the discount rate, 0.075 into 1 minus 1.075 to the power 50, and that equals 12,974 and 81 cents. So that's all this money being moved back to today has a value of 12,974. Of course, if you take the undiscounted value of that money, then that would be, for 50 years, that would be 50,000. So it is not 50,000, it is rather, the present value is 12,974. And to find the value of this 50 years from now, you're going to take this amount, 12,974.81, and you're going to multiply it by 1.075 to the power 50, which will give you 482,530. So that's what you're going to have at the end of 50 years. Now that is a considerably larger amount than $50,000, and maybe this will inspire you to start saving. Next, we are going to look at amortized loans. And amortized loans are loans where the borrower repays interest and part of the principal every period. Now, these are very common loans because, especially for consumers, because you think of consumer loans, and most consumers, when they take loans to, they buy things like houses or cars, and they are usually salaried, so they have an earning every month, and so they are able to pay a fixed amount every month. So, and of course, the lenders prefer that instead of saying that, you buy this house and you give me back your entire borrowing at the end of 30 years, which will be too risky. They would rather that the borrower keeps repaying regularly. So we are going to work through an example of an amortized loan just to show you how it works. And here we have a borrowing of $10,000 today. You're also told that the interest rate is 8% and the loan is going to be repaid in 3 equal installments of $3,880.34. So how will this work, and why is it that this repayment amount is the correct repayment amount? So let's work through this entire amortization, and then you'll understand. So when you start the first year, what is the outstanding principal? Well, the outstanding principal is the amount which was borrowed, and that is 10,000. What is the interest on this principal? Well, the interest should be the outstanding amount multiplied by the interest rate. And that interest rate is 8%. So 8% of 10,000 will be 800. So the borrower repays 3880, whereas the interest is only 800. Why does the borrower repay 3,880 instead of just 800? Because the borrower is also repaying the loan. The borrower is also amortizing the loan. Hence the name amortized loan. So every period when the borrower makes a repayment, there is the interest is of course paid, and after that some of the principal is also paid down. So, and what is the amount of principal reduction? How much principal is paid down? Well, that is going to be the amount which the borrower pays, which is 38.80 and 34 cents minus the interest amount. So this 800 does not go towards paying down the principal. It is simply interest for that first year. So the amount of principal reduction, the amount of principal repayment would be the total payment minus the interest amount, and that is equal to 3,080 and 34 cents. So what is the principal outstanding at the end of the first year after this repayment has been made, which is also the principal outstanding for the beginning of the second year? Well, you look at the starting principal. From that you subtract the repaid amount of principal, which is 3,080 and 34 cents. So from 10,000 you subtract this, and you get the ending principal for the first year as 6,919 and 66 cents. So the loan started out as a $10,000 loan, and after the first payment has been made, the amount remaining to be paid falls to 6,919 and 66 cents. Of course, as the borrower does not repay this entire amount at the very beginning of the second year, there will be additional interest which shall be added on. But this is how things pan out at the end of the first year. The principal amount has gone up from 10,000 to 6,919 and 66 cents. So the principal at the end of the second year is 6,919 and 66 cents. Now, to find the interest, you're going to multiply this again by 8% or 0.08, and that is going to give you $553.58. So the interest payment for the second year is $553.58, which makes the principal reduction equal to the amount which the borrower repays, minus the interest payment. So that is going to be, again, the borrower repays the same amount the second year, which is 3,880 and 34 cents, minus the interest amount, 553 and 58 cents. So that gives you $3,326.76. So this is the principal reduction. So the principal at the end of the second year, you're going to get by taking the starting principal, subtracting the principal reduction, and that will equal 3,592 and 90 cents. Now, this ending principal at the end of the second year is also the starting principal for the third year, and is also the amount on which interest is going to be calculated for the third year. So, interest for the third year is going to be this amount, multiplied by 8%, and that equals 287.44. You can just use a calculator to verify these numbers that I have here. When you multiply 3,592 and 90 cents by 0.08, you should get 287.44. And then you will have the principal reduction to be the repayment for the third year, the amount repaid in the third year, which is 3,880 and 34 cents, minus the interest payment for the third year, which is 287 and 44 cents. And guess what that principal reduction is going to be? Well, you just do the subtraction and you're going to have 3,592 and 90 cents. So principal reduction for the third year is this amount. What is the starting principal for the third year? Well, the starting principal was this, and they both happen to be equal. It means the ending principal for the third year is going to be a big zero. So that is what makes these payments of 3,880 and 34 cents the correct amount to be repaid for this amortized loan, because if these are the repayments, as we have seen as we work through this example, the ending principal becomes zero at the end of the third year, which is the point of an amortized loan. The repayments are supposed to pay both interest and also pay down the principal amount. And you can see the principal amount here has been paid off. Now, in this example of amortized loan, what we did is that we said, okay, there was this amount, 10,000. You can think of it as the bank had initially invested with the borrower, and the borrower was giving the bank a return of 8%, and then we were moving forward through time, and we were seeing how the remaining principal was earning a return of 8%, and the payments were paying off the principal till at the end of the third year, we were left with the zero remaining principal. So when we did that, the way we proceeded was moving forward through time. Here what we're going to do is, we're going to use the annuity formula, which actually discounts back payments. And if you are asked, what is the value of a 3-year annuity with yearly payments of 3,880 and 34 cents, well, you'd use the annuity formula to answer that question. So you would say 3,880 and 34 cents divided by we keep the same rate, which is going to be 8% or 0.08. So we'll divide this by 0.08 into 1 minus 1.08 to the power 3. So this is 1.08 to the power 3. And this, if you solve it, is going to give you 10,000. So what does this tell you? What it tells you actually is that when you have these cash flows, you have these three cash flows of 3,880 and 34 cents. Then you can think of the present value as something that you had invested, and this paid off that investment at an 8% rate of return. So that was moving forward through time. Or you can use the formula to move back in time, which is discounting. Use the annuity formula, and they both give you the same answer, which says that these three cash flows, if the rate is 8%, have a present value of 10,000. Whether you solve it thinking of it as a rate of return, so you move forward, or you solve it using the annuity formula, which is for a rate of discount, which is moving back. So this is an example of the equivalence of rate of return and rate of discount. If your rate moving forward and the rate moving backward are the same, then you will have the same present value, whether you think of it as an investment or you think of it as the present value of some cash you're going to get in the future.